Okay, so like yesterday, we are going to discuss the homework problems first, and you need to show me what you have done. So quickly, one by one, show me what you have done for the rest of the homework problems.
Yes, ma'am. Ma'am, is it visible?
Yes.
Ma'am, first is transforming x, y, z to EDN.
No, no, I said NED.
NED.
Hmm.
Oh, so x should be n.
X should be N.
Okay, I
What
can do
you have
that.
done? Yes.
I've x equal to e. I've done.
Then also it is not a. Is it a right-handed frame? EDN. Did you check
Uh,
that? It has to be, otherwise you cannot
yes, ma'am.
create.
Yes.
But we don't have any such frame. Okay, either we have ENU or NED as per
Oh,
convention. Okay, but show me what you have done.
yes, ma'am. So from x to e, we have to move lambda plus pi by 2.
Okay.
So x would come there.
Mm.
Then y and so step 2 is there is no rotation required over y because it is already aligned. And
It is already aligned. Okay,
yes,
E is
ma'am.
along. E is along. Sorry, X is along E. East.
Yes, yes,
Then
ma'am. N and D are along y and z, so we don't need rotation along y. It looks like this from the side.
But I do not think so because see, not this plane is not the same as the equatorial plane. You are at some latitude. There, the northeast plane is different from the equatorial plane. If you say that x is aligned along north and east along y, then it is the same as the equatorial plane. You are in the equatorial plane, right? X and y are in the equatorial plane, right?
Yes, ma'am. Yes, ma'am.
But northeast plane is different from the equatorial plane. Then next,
Then in order to align the YZ with the down north, I put phi equal to minus L. So this would go this way
so you are doing this rotation about which axis?
about x-axis.
Then E will change, right? You have already oriented Y along E.
No, x along E. X is along E.
Oh, X along E, okay.
Yes, ma'am. Yes, ma'am.
Uh, X along E, oh, then you are saying Y along N. But
Z would be along N, Y along D. Minus Z rotation downward.
no, I'm not asking about the final thing. Here, the intermediate orientation. So here you are showing X is along E and Y along north. That
North and down.
that is
These two are the same figures.
but then they are not in the equatorial plane, right? Northeast
Yes,
plane
ma'am.
is not the equatorial plane, so there it seems there is something wrong. But then, if I assume that okay, north and east are oriented that I mean x and y are oriented that way. After that, what you are doing? You are applying a rotation about x, roll
Yes, ma'am.
rotation, roll about x. That will orient.
This way.
But the angle between what is the angle you have taken? Angle between then after this rotation, Z is along north.
Yes, ma'am.
But that intermediate thing is not right. They are not along north and east.
Understood, ma'am.
That you have to correct. And the final frame has to be NED. Okay.
Got it. Yes, ma'am.
Okay. Next.
Uh, Next one was we had to prove that eigenvalue is 1.
No, that we already discussed in the class, right?
Okay,
That
okay.
equation itself tells that eigenvalue is equal to 1, right? One of the eigenvalues is equal to 1.
Okay, ma'am, I done it. It's fine.
Okay.
Then we had to find coordinate transformation matrix for roll and pitch. So
Okay, I
what?
did not expect you to do that. You have done it fine. I do not want to see this. Okay, fine.
Then then we have to prove that C beta alpha
Hmm.
has three
Yes.
degrees of freedom.
Yes, yes, yes.
I said that C beta alpha is the roll matrix times the pitch matrix times the yaw matrix.
Hmm.
And I said the let this be A, B, and C.
Hmm.
Now, matrix A has only one degree of freedom because for a given value of phi, all other terms are fixed. And
Okay.
this and the same argument for B and C. For a given value of theta and for a given value of psi, the matrix terms are fixed.
But how can you say that the product will have 3? Each elementary matrix has 1 degree of freedom, but okay, they are independent.
Yes, ma'am. I
But they
wrote.
are about not independent. Okay, but they are not about the collinear axis,
Yes,
non-collinear
ma'am.
axis. So that way you can say 3 degrees. Okay, fine. Without using Euler angles, also it can be proved. Okay, then next.
Next one was if we are given y beta alpha
Yes.
x beta. Here I did not get how to do it, but I think we need to use the eigenvector z beta alpha for such that this is equal like
But
z beta.
eigenvector, how will you find the eigenvector if you do not know the matrix itself?
Yes, ma'am. That's where I got stuck. So I didn't know how to
You have
proceed.
to do it using x and y. You have been given only x and y, right? Okay,
Yes,
fine.
ma'am.
Anything else you want to show?
No, no, that's it.
Okay, fine. Who will explain next?
Thank you, ma'am.
Explain quickly. Who wants to explain next? Nila?
I tried, but I wasn't able to do them.
No, but you should at least show what you tried. Simply do not say you have tried and you couldn't do. You need to show what you have tried. Krishna, you are showing something yesterday.
Yes, ma'am. It was eigenvalue is 1. I'm
Eigenvalue
on.
is one. That only you have done.
Yes, ma'am. I tried that transformation from EF to NED, but that was not correct. Yesterday you said, ma'am.
Nothing else have you done? 3 degrees of freedom.
No, ma'am. I tried, but I'm not getting.
No, see, don't say you tried, you are not getting, or you should show what you tried. Sujit, do you have anything to show?
Yes, ma'am. Ma'am, it is visible?
No. Now it is visible.
No. Okay. Uh, this one is the
No, but I can't see what you. Have you emailed me? Have you emailed me?
okay.
Okay means what? I told you to email what you are going to explain before the class. What is that okay? Show me quickly. I'm not able to see what you have done. I'm just seeing some files. This way time gets wasted. Every time the same thing happens. This is why I told you to email me your answer before the class. So I would assume you have done nothing. Should I assume you have done nothing?
Ma'am, second one is this one.
I'm not able to see anything. So if you do not send me what you have done before the class, I would assume you have done nothing, because this way I cannot waste time. It will not come and I'll keep waiting. This way it is not possible, okay? So if you do not take my word seriously, I would assume you have not done it, okay? I'm just giving you 1 minute time. Within a minute, if you can show me what you have done. Nothing is visible. I'm just seeing some files are there, but
1 minute.
next time I'll not give you this 1 minute also, because I clearly told you to email me your answers so that I can see them on my screen.
This image is visible, ma'am, or not?
No. Really, have you done anything?
Yes, ma'am. Download image. This one, ma'am.
Yes.
Yes.
Enlarge it. Enlarge it.
Find the.
Enlarge
Yes.
it.
Okay.
I'm not able to read anything. You need to increase the font size.
Now, ma'am.
What are the rotations you have applied? L and lambda, it's not correct.
Lambda and L.
So lambda and L means what? Lambda about which axis, in what direction? This is not correct. But lambda and L about which axis you applied?
L about x-axis and lambda about y-axis.
I cannot see the figure properly. L about x-axis, y-axis. Just scroll up a little bit. See, this way I will not be able to understand anything. You have network issues, that's why I told you to email me your answer. It is not correct. Next time I will not see if you do the same thing. You must email me your answer and then only I'll see what you have done. This way I will not be able to understand anything. Next, quickly tell me.
1 minute.
No, I'll not listen to you, Sujit. I gave you enough
Yes.
time.
Yes, ma'am. This is this one.
Tell me what you have done.
Yeah, ma'am.
It
This
is
one
not.
is.
It is not visible properly. But you tell me what you have done. What exactly you are trying to do here. Now I did
Yeah.
not ask you to prove this roll and pitch. I just told that you should do it. Next.
This at this one only, ma'am.
You have
Two
not
from.
done anything else.
No, ma'am.
Fine. Murali, have you done anything?
Yes, ma'am.
Yeah, show me whatever.
Ma'am, I couldn't attend the last tutorial class because I was not feeling well. So yesterday I tried all the previous tutorial problems. And today morning I rewatched the last lecture. So I tried a couple of problems in the last tutorial problem. So I'll
Yeah,
share
but
my
you
screen.
should. Yeah, sure. But we
Ma'am,
already discussed few things yesterday. I do not want to see those things. So whatever we discussed in the class, I do not expect those things to be explained again. That doesn't make any sense.
yeah,
So
okay, ma'am.
do not show me anything that we already discussed.
Okay, ma'am. So this one,
No, we
so
already discussed this in the class. I do not want to look into this.
okay.
This also we discussed
This
in the
also we
class.
did, yeah. Yeah, so from
What is
yesterday's,
this?
yeah, so this for pitching and rolling, right?
So pitch and roll I did not ask in the class. If you are done, fine. Then next.
Then I took the transformation matrix. So I have the same argument. So I got the three matrices. So so for the first one, if you fix a psi, so you'll have one unknown, and so in that way you will end up having 3 degrees of freedom. So
Okay.
I multiplied them,
Three
and
and one unknown. Okay.
but yeah. So for the first matrix psi, second one theta, third one phi. So I tried multiplying them in the reverse way, so to prove that the inverse is the same. So yeah,
That was also discussed
I
in the
asked him.
class. Next.
Yeah, so the remaining problems I couldn't visualize, ma'am. I'll try again.
You will keep trying till the end. You will try again means we are
No,
going
ma'am,
to discuss all the problems today. I cannot give you infinite time to think about it. Anyway, fine. Okay, we are going to discuss. Nobody did this, although I told you repeatedly what you have to do, and it is quite simple. That CD is equal to RD. Ignore this thing. This is from the previous problem. So here we need to prove that CD is equal to RD without using the mathematical expression of RD, and it's quite simple. So basically we need to make use of this relation between linear velocity and angular velocity. We know V is equal to omega cos R. For circle, R is the radius, V is the linear velocity which is tangential to the circle, and omega is perpendicular to the circle and away from it. So I have shown the directions. This is R radially outward, V, and then omega is perpendicular to the page and away from it. So V is equal to omega cross R. This actually we are going to apply this simple formula for different base fitting circles. So the first base fitting circle we have is the circle in the north down plane. So we already discussed that the radius of the base fitting circle in the north down plane is Rn, right? So just imagine that base fitting circle in the north down plane and its radius is Rn. So for this circle, we must have some linear. We already have linear motion, right? Linear velocity component. So we also have to identify the corresponding omega and r. We know r is Rn, and it is about negative down axis. So this is the down axis, and we are considering r in this direction. So Rn is about negative down axis, and then In. So the velocity which is tangential to the base fitting circle in the north down plane is basically N component, not component of the velocity vector. This is what I have written EB, and this is the north component of that velocity vector. I have put this arrow over it because we are considering the direction as well. So this is along north. And then what is the angular motion, the angular velocity, corresponding angular velocity? We know that for north-south motion, the latitude changes, right? So the angular velocity must be L dot. and we can easily see that L dot, which is a vector, which is actually in this particular case, if you think that the page is the north down plane, it is perpendicular to the page and away from it. This is the direction of L dot we already discussed in the class yesterday. Now, what is the direction of east? So this is north, this is down, which are on the plane of the page, and east must be perpendicular to it and into the page. So that is the direction of east. Whereas we see that L dot is perpendicular to the page and away from it. Therefore, L dot is along negative east or along west. So we have minus C minus D y cross Z. Um, so that will give X. Right, so from this is the relationship that we have for the base fitting circle in the north down plane. Right. How about other base fittings? We have to. We can also consider an east-west circle passing through this point, and we can also consider the best fitting circle in the east down plane. Right. So let's see what we can say with those circles. So let's consider the east-west circle passing through this C point. Okay, east-west circle. Now we already proved yesterday that small r is the radius, and this angle is L. So small r is equal to CD cos L, that we already discussed in the class yesterday. And what is the angular velocity associated with this? As the point moves in the east-west direction, longitude changes. So the associated angular velocity is lambda dot. Therefore, we can apply this equation for this east-west circle, and V must be in the east direction, east component of the velocity. So we have the east component of the velocity, lambda dot cross r. And we already found from geometry that small r is equal to CD cos L. We did not say anything about CD, we just showed that CD is this length. Now next, consider the base fitting circle in the east down plane at C. East down plane, so we need to pass a plane containing the east and down axis, right? And then find the base fitting circle in the east down plane. What is the linear velocity tangential to that circle? It must be along the east direction. So we have to take the east component of the velocity here. What is R? R is the transverse radius of curvature, because we are considering the base fitting circle in the east down plane, and the corresponding radius is the transverse radius of curvature by definition. So we have to take RE in the corresponding equation. This will be the east component, this will be RE, and east component is along east, and then RE is along negative down axis. Next, we need to identify the corresponding omega. What is the corresponding omega? Now we already know that L dot is along east, negative east. So L dot does not have any contribution, because we need to pick the angular velocity which is perpendicular to the east down plane, and we already know that L dot is along negative east. So L dot does not have any contribution. What is the other angular velocity we have? Lambda dot. Lambda dot is this one actually, right? The lambda dot can be resolved into two components, one along north, another along negative down. This angle is L. So along north we have lambda dot cos L, and then along negative down we have lambda dot sin it. But again, the circle is in the east down plane, and we need to pick a component which is perpendicular to that circle. So lambda dot sin L will not have any contribution. It is only this component lambda dot cos L along north, which is perpendicular to the base fitting circle in the east down plane. So that is the required angular velocity, omega 1, and it must be along north as per the convention. And just now we showed that lambda dot cos L is this angular velocity. So we, from the east down plane, we get this velocity is equal to lambda dot cos L cross RE. Now if we just consider the magnitude, from this equation we have east component is equal to lambda dot cos L into RE. And then from the east-west circle we get the east component is equal to lambda dot into CD times cos L. So just compare this two and you'll see that CD is equal to RE. So without using any formula, any mathematical expression of RE, we can prove that CD must be equal to RE. Therefore, that length is actually the transverse radius of curvature. This is clear to everyone? How we could justify that CD is equal to RE?
Yes, ma'am.
Okay, next, see the coordinate transformation matrix has 3 degrees of freedom. So you can use Euler angles without using Euler angles also it is possible. You just use this formula CC transpose equal to I. From here we get 9 equations and we know CC transpose is a symmetric matrix. So symmetric matrix means we have the off diagonal components are given by this, right? And then on the right side of this equation we have identity matrix. So if we equate each component, each element of the true matrices, we get 9 equations. But since we have a symmetric matrix, 3 equations will be identical. So actually we have 6 different equations. 6 different equations, 6 independent equations and 9 unknowns. Here we have 9 unknowns and 6 independent equations. So 3 of the unknowns we can choose freely. So this is another way of proving that it has 3 degrees of freedom. Once we choose any 3 elements, the other 6 elements are automatically defined by these 6 independent equations. So they are constant. This is why we can say that the coordinate transformation matrix has 3 degrees of freedom. Okay. Next is this one. So we have 2 non-collinear vectors y and x. See here what we need to do is we need to pick a column in such a way that that column is not collinear with x and y. One way to do that is to just take the cross product. We know that cross product is perpendicular to the both vectors. So just take the cross product this side and similarly you also have to take the cross product on this side. Then this will be an invertible matrix and you put it on the left side. And this matrix is also known because we know these 2 vectors in the gamma frame. And inverse of this matrix times this matrix is actually the coordinate transformation matrix. Okay. This has an important practical application in INS. Using this approach, we can find the body frame or sensor frame orientation with respect to the northeast down frame. What is done is using gyroscopes and accelerometers when the vehicle is stationary, we can find the acceleration due to gravity. So when the vehicle is stationary, not moving, then the accelerometers read the acceleration due to gravity. Okay, and we know that acceleration due to gravity is along the down axis. And the accelerometers, 3 accelerometers are there, so they are mounted in certain directions on the body. So each accelerometer will sense the corresponding component of the local gravity vector along its sensitive axis. So this way we actually get the acceleration due to gravity resolved along the 3 sensor axes along which the accelerometers are mounted. Now, this is the earth rotation rate. We know that the earth rotation rate vector is along the ECXZ axis. We already know that this can be resolved along north and negative down. For a stationary vehicle, the gyroscopes measure the earth rotation rate. Okay. And again, just like the acceleration due to gravity, gyroscopes would show the components of this omega vector along their sensitive axis. So basically, and from theory, we know in the local navigation frame along which direction these two vectors are pointed. So we know that acceleration due to gravity is along down axis. Then the earth rotation rate has one component along north, another component in this direction. So we know X and Y in the local navigation frame. We know them in the sensor frame because the gyroscopes and accelerometers of a stationary vehicle measure them. And then if you take the cross product and put that in these columns, so this is basically the coordinate transformation matrix from sensor frame to navigation frame. Now we can go one step forward. Instead of putting what the gyroscopes and accelerometers measure in the sensor frame, we already know the orientation of the sensor frame with respect to the body frame. So we can do that transformation. So we get the measurements in the result in the sensor frame, and then if we multiply the sensor to body coordinate transformation matrix, we can find them actually in the body frame. So we can have this result in the body frame also, and then using this approach straight away we can get the body frame to local navigation frame transformation matrix. Okay, so this method has a practical use. It is done for attitude initialization of INS when the vehicle is stationary. By using the gyroscope and accelerometer measurements, we can find the body axis orientation with respect to the local navigation. Okay, fine. Next, this rotations. Basically, you are supposed to find the rotation such that the pitch rotation does not exceed 90 degrees. So here I am showing the north, east and down frame, and this is the X, Y and Z. You see X, Y and Z, and this one is the equatorial plane. So this is the meridian plane which contains the point of interest. Okay, so this angle is L, latitude, and this is longitude, lambda. First what we will do, we will apply your rotation of 180 degrees minus lambda in the negative direction. So here I have shown the direction. So positive rotation is from left to right, whereas here we are applying a rotation from right to left. That's why I put negative sign. So right to left, negative rotation of magnitude 180 degrees minus lambda. What will happen after that? X-axis, this is the X-axis. After the rotation, the X-axis will be oriented with this bold line in the equatorial plane. This one. So this will be the new orientation of the X-axis after applying the rotation about the Z-axis. Since we are doing the rotation about Z, Z prime remains the same as Z, and Y will also be rotated in this direction from right to left. Let's say this dash line shows the Y axis, new Y axis. Okay. Next, what we'll do, we'll apply a pitch rotation. Now, you should also note that this X prime axis, this is in the meridian plane. And north and down axis, they are also in the meridian plane. So X prime is actually in the meridian plane. Z is always, Z is the axis of rotation, it is always in the north down plane. So both X prime and Z prime, they are in the north down plane. And Y prime must be perpendicular to the north down plane, which means Y prime after this rotation is along negative east. So this is the direction of east, and Y prime is perpendicular to the north down plane after the rotation. So it is along negative east or west. Okay. Next, we are going to apply rotation, pitch rotation about this y prime axis so that the z is along negative down. So to apply the rotation, we need to know the angle between z-axis and the down axis, right? So for that purpose, what we can do, we can shift this point or this line here without changing the orientation. We just shift this left so that this point is at O. And this is what is shown in this figure. We know this angle is L. So L is the angle that this line makes with the horizontal. Then this angle must be 90 minus L, which is the angle between the down axis and the Z. So we need to apply a rotation of this angle so that the Z is aligned with the down axis, but it will be in the negative direction. What is the direction? So will it be positive rotation or negative rotation? So using the right hand thumb rule, you can find out whether it is positive or negative. The positive rotation will be from right to left. This is the y-axis. It will be from right to left. But here we need to go in this direction, in the opposite direction, from left to right. Therefore, we need to apply a negative rotation about the y prime axis. So there will be a pitch rotation of minus 90 degrees minus L. So that Z is along the negative down axis. When Z is along the negative down axis, automatically X will be along north, because you just imagine shifting Z. Similarly, X will also be shifted and Z is along this direction. Since both of them are in the north down plane, X prime must be along local north. How about the pitch constant? We know the point is in the northern hemisphere, so L is less than 90 degrees. We are not considering pole. L is less than 90 degrees and positive, therefore this angle is less than 90 degrees. So we have satisfied the pitch constant. But after this, X is along north, Y is along west, and Z is along negative down. So we need to apply a roll rotation of magnitude 180 degrees so that Z is along down and Y is along east. So we need to apply 3 rotations, yaw rotation first, pitch rotation, and then roll rotation. So when you are writing the rotation, you need to show the direction and magnitude, both. Otherwise, your answer is incomplete. Clear? Any question? Fine. Okay. Since we have time left, we'll continue the discussion of attitude. So let me set things up for that. Uh, so we were discussing the coordinate transformation matrix. Uh, we are going to talk about one more thing about the coordinate transformation matrix, and then note the advantages and disadvantages of this method. Uh, Now we already derived this. This is the time derivative uh, derivation for Euler angles. Uh, Now here I just want to make a comment because we need to use this for the derivation. Next we are going to derive the time derivative of the coordinate transformation matrix, and for that derivation we require something from here. Okay. So here we found the relation between P, QR and this Euler angle derivatives. Now just imagine that all these angles are very small. So for small angles, we can say that this phi dot and P dot. So for small angles, we can say that phi dot is equal to P, which we are getting from this side. Similarly here, just imagine all of these angles are infinitesimally small. So these axes, they are actually not different from one another. So theta dot and Q, so theta dot actually equal to Q. Similarly from here, this side we are getting psi dot is almost equal to R. This is R. So this yellow line and this green line, they will be almost coincident. We can say that psi dot is equal to R. Okay. This is one thing we need to use. Another one. Here. So here what we have done, we have found the coordinate transformation matrix from the three other rotations, right? Now if you multiply the three coordinate transformation matrices, you get the resulting matrix. How about the case when all these angles are very small? We need to do small angle approximations. So cos theta we can write equal to 1, sin theta we can write almost equal to theta. And then all the three matrices we need to multiply. And since all the angles are infinitesimally small, we can neglect the higher order terms and keep only the first order term. Right? So if you do all these, you will find that for this small angle approximation, the resulting matrix, the coordinate transformation matrix, is actually this. And then from the time derivatives of the Euler angles, we found that um, the roll rate So this you can write as this one. So you can write phi is equal to the small angle is delta t, and then in place of phi dot we can write right. So if we substitute this here, we get so there we had minus theta and put delta t outside. We are just write omega 2. So omega is basically omega beta alpha alpha. Okay, since we do not have space here, I am just writing omega. And then here we had phi, so omega 1, here minus omega 1, here omega 3, this is what we get, right? This we can write as, so this is the expression we are getting for small angles. So we will take out the identity matrix, the diagonal terms, and then the rest we will put this way, 0, since we have put negative sign before, we need to reverse the sign. Okay, now this omega is nothing but this omega. Okay, so this we can write as the skew symmetric matrix. This is a skew symmetric matrix. This we will write as capital omega. And since the small omega is actually beta alpha alpha, in the capital omega also will follow the same convention, because the elements of this capital omega matrix, if this is a skew symmetric matrix, this is not a vector. And the elements of this skew symmetric matrix are formed with this vector beta alpha alpha. So beta is the reference frame, alpha is the object frame, and this alpha on top is the resolving frame. The same convention is followed for the capital omega matrix also. Okay, so this is the expression that we get for small Euler angle rotations. Okay, we are going to make use of this to find the time derivative of the coordinate transformation matrix. We are actually interested in finding an expression for this. Because if the attitude changes over time, we need to find the coordinate transformation matrices over different points in time, right? For that we need the derivative, just like Euler angle time derivatives, we also require the time derivative of the coordinate transformation matrix when attitude is changing. So here we have the beta frame. We assume that it is fixed, it's not changing. And then we have another alpha frame, object frame. Let's assume that the alpha frame is changing its orientation relative to the beta frame as time passes. Okay, so this is let's say the orientation at some time instant t. Okay, then let's take another time instant t plus delta t. So at this time instant, alpha frame will have another orientation. So let's say, and delta t is very small. Okay, so it will have some other orientation. On that we can write. So at this instant, so this is the transformation matrix at t. And similarly, at t plus delta t, we have another transformation matrix. Okay. So this is the coordinate transformation matrix from beta frame to alpha frame at t plus delta t. Now, can't we write it this way? We know that by multiplying the coordinate transformation matrices from right to left, we can account for successive rotations, right? So let's say that this is the coordinate transformation matrix from beta to alpha at t, and then we go from alpha at t to alpha at t plus delta t. So that will be alpha at t to alpha at t plus delta t, right? So what will be the expression of this one? That we already proved. I mean, derived. We already derived an expression of small the transformation matrix for small Euler angles using the rotation, the angular velocity vector of the alpha frame, right? So we can use this maybe delta t will be there. Right? So let's use this expression. Right? Now the derivative as per definition is so substituting for this one. So this term cancels out, and then delta t will also be cancelled out. Okay, so this is the formula for the time derivative of the coordinate transformation matrix. And since this does not depend on the transformation matrix, it's basically formed, this capital omega matrix is basically formed with the small omega vector, right? The angular velocity vector. So differential equations are linear. You have 9 elements, right? So 9 differential equations will be there. But unlike Euler angle differential equations, which are nonlinear, here the differential equations are linear. Okay. Any question? So let's note the advantages and disadvantages of the coordinate transformation matrix. There is no singularity. Suitable for mathematical competitions, because we can do everything that we require. We can account for successive rotations. We can go from one frame to another frame, change the resolving frame also. Not only attitude, we can also change the resolving frame of a vector. So this is suitable for mathematical operations. Disadvantages, and then also as linear differential equations. Disadvantages are that we need to deal with 9 differential equations. And this is not intuitive. So to visualize rotations, we need to calculate Euler angles, and then only we can have some insight into how the transformation is happening. Otherwise, it becomes purely mechanical. We just do the computation. Unless we calculate the Euler angles, it is also possible to calculate the Euler angles, okay, from the coordinate transformation matrix. We didn't discuss this in the class, but given a coordinate transformation matrix, we can also find the Euler angles, and then using the Euler angles only we can visualize the rotations. So that's it about the coordinate transformation matrix. Next, I'll quickly mention the other two methods. I will not discuss anything in detail. The next two methods are quaternions and rotation vectors. I'll first talk about the rotation vector, and then I'll explain the quaternions quickly. So what is a rotation vector? While discussing the eigenvalue, I noted that instead of applying 3 successive rotations, if we apply just one rotation, single rotation with a suitable rotation angle, we can go to the resulting frame. And the axis about which we apply this rotation is called the axis of rotation. And the angle by which we need to do the rotation is the angle of rotation. The rotation vector it is denoted as rho beta to alpha. So we are going from beta frame to alpha frame. It is actually a vector. So the axis of rotation, the unit vector along the axis of rotation, and we know that the unit vector the axis of rotation is invariant in both the frames. Whether we resolve it in the beta frame or alpha frame, we get the same components, right? So E is the axis of rotation, and then we multiply the rotation magnitude. Let's say that we have applied the rotation of magnitude theta, the angle of rotation is theta. So this is the rotation vector. We have the unit vector along the axis of rotation, and then the magnitude of rotation is given by theta. Okay. Now the rotation vector has a unique advantage that other methods do not. What is that? It allows us to interpolate attitude. Rotation vector allows interpolation of attitude if the axis of rotation is not changed. The other methods do not allow us to do this, even if the axis of rotation is not changed. So let's say we are going from beta frame to alpha frame. So beta is the initial frame, alpha is the final frame, and we are applying about the axis of rotation, we are applying the rotation. Okay, at some intermediate point, we have applied a rotation uh, by angle, let's say k theta, and k is greater than 0, less than 1. So we have not gone to the alpha frame yet, right? But with this k theta rotation about the axis of rotation, we get an intermediate frame beta, gamma. So the rotation vector for that frame is beta gamma. Since the magnitude of rotation is k theta, we write k theta, and then the axis of rotation is not changed. This is the rotation vector for the intermediate frame gamma. And then if we keep applying the rotation, then we go from gamma to alpha with the rest of the rotation. And the rotation magnitude is this. Right? So if we add these two, we basically have this one, which is nothing but the rotation vector from beta to alpha. Right? So our objective was to go from beta to alpha frame, but in between we could also represent the gamma frame. This is why it is said that it allows interpolation of attitude. But you cannot do this addition. You cannot do this addition if the axis of rotation is changed. The addition is allowed when we have collinear rotation vectors. So these two vectors, they are collinear actually, same axis of rotation. But if we have two non-collinear rotation vectors, then we cannot do addition. Then we don't think that this will give this vector. So for two non-collinear rotation vectors, we cannot do the addition. we cannot say that this is equal to this one. Okay. Next term, see about the rotation vector. Let's say we have applied a rotation of 2 pi about the axis of rotation. What do you think the final frame would be if we apply a rotation of 2 pi? What will be the final frame?
It will be same. We will come back to the old position.
Yes, we get the same frame, beta frame, right? But what is the corresponding rotation vector? We have a rotation vector, right? The rotation vector will be, instead of 2 pi, I am just making it more generic, 2 and pi. And we can also put plus minus 2 and pi, small, right? So we are applying a rotation. This is a rotation vector, but we are getting the same frame, beta frame. Right, although we have a different rotation vector, we cannot say, as per the convention of the vector, we cannot say that this is not a rotation vector. We are applying a rotation, we have a rotation vector, but we do not get a different frame, we get the same frame. This is why it said that there is a singularity at plus minus 2 and 5, because we do not get a different frame, we get the same frame. Although we are applying rotation, we get the same frame as before. Okay. Now, like Euler angles and coordinate transformation matrix, the rotation vector also has its time derivative, but we will not go into that in this class. Okay, and the differential equation, only one, the differential equations are non-linear. So quickly I will write the advantages and disadvantages. Uh, Under advantages, you can say that here we have three differential equations. The disadvantages, the differential equations are non-linear. Then there is a singularity at plus minus 12. Okay. Next one is quaternion attitude. Quaternions actually use the axis of rotation and magnitude of rotation just like the rotation vector, but represent them in a different way. A quaternion is a hypercomplex number with 4 elements. Okay. So it has a scalar component. There are different ways we can represent a quaternion attitude or a quaternion. Q is the standard notation. Okay, so this denotes we are going from beta frame to alpha frame. Okay, and we have a scalar and a vector. So we have this beta and alpha frames, and we are applying a rotation of magnitude theta. Then the scalar component is given by going from beta to alpha frame. This is the scalar component. Okay, and then the vector component has the 3 elements of the rotation. The axis of rotation. It does not matter whether you resolve in beta frame or alpha frame. That's why I am writing beta or alpha. So whether you resolve in beta frame or alpha frame, you get the same component. And then here sine theta by 2. I'm dropping the subscript, okay? Sine theta by 2. Theta by 2. This is a quaternion attitude, okay? Now quaternion math is completely different, okay? So quaternions have completely different mathematical rules. There is a separate chapter on this. It's called quaternion algebra. So if one wants to do attitude computation with the help of quaternions, one has to learn the quaternion algebra. Okay, so they have different product rules. Okay, things are handled differently in quaternion algebra. Now you may ask why such a complex representation. See, if you apply this 2n pi rotation, what happens? So 2n pi rotation, just consider 2 pi. No need to do 2n pi. If you do 2 pi rotation, so theta is 2 pi. Theta is 2 pi. What happens? So this becomes cos pi, right? And this all these 3 components, the components of the vector will have sin pi. Now we know that sin pi is what? Sujit, sin pi is what? What is the magnitude of sin pi?
Sin pi is 0, ma'am.
Sin pi is 0. So here we are basically getting this. This has magnitude 1, but all the 3 elements, other 3 elements are 0. So basically there is no vector. If we do not have any vector, then we do not have any rotation, right? So there is no singularity at plus minus 2 and pi. So with this quaternion representation, we can get rid of, although we are using the same components of the rotation vector, we get rid of the singularity. The quaternions do not have any singularity because the vector components, they become 0 when we apply a rotation of plus minus 2 and pi. So there is no singularity at plus minus 20. Okay. We'll not get into quaternion algebra in this class. We'll quickly note the advantages and disadvantages of quaternions, and that will be the end of the discussion of attitude. Uh, uh, Quaternions will also have their time derivatives, and it can be shown that the equations are linear. So basically we have 4 linear differential equations. Okay, this is suitable for mathematical computation. No singularity. Now, unlike the coordinate transformation matrix where we have to deal with 9 elements, here we have 4 elements. Okay, so this is a compact representation compared to the coordinate transformation matrix. Okay, the disadvantage is non-intuitive. Since we need to handle the mathematical operations differently, unless one is comfortable with quaternion algebra, there is a chance of making mistakes. Okay, it's non-intuitive, and therefore to visualize rotations, Euler angles have to be calculated. Then only we can visualize rotations, and if one makes mistakes and one is not comfortable with the quaternion algebra, it's difficult to find out where the mistake is. Okay, so that's all for today. Do you have any question? Tomorrow we have the first class test from 11 to 12:15. 1 hour 15 minutes. I already sent you all the rules for the class test. You need to follow all the rules. Okay, and the question paper will be posted on Microsoft Teams at 11 o'clock. You need to turn on the camera during the exam in Microsoft Teams, and within 10 minutes of the exam you need to send me your answer. I'm not going to consider your answer after that. And make sure you name the file correctly. All the pages are proper, the file opens. This is your responsibility to make sure the file opens properly. And the file format should be either JPG or PDF. Do not use any other format. Okay? Any question about the test?
Ma'am, what is open note?
You can refer to the lecture material.
Okay, ma'am.
And after the test, we'll discuss the questions. Okay? Anything else you want to ask? That's all for today.
Thank you, ma'am.
Thank you, ma'am.